This is CS350. I'm Karthik Gopalan. In this lecture, we will talk about memory management, which deals with how the operating system divides up the physical memory among multiple processes running on a computer. In the ideal world, programmers would want lots of memory in their computer. They would want the memory to be accessible very fast, and ideally they would want that if any amount of data is written into the memory, it stays in the memory when you power off the machine, which means that it is persistent. So the three desired properties are that memory should be large, fast, and non-volatile. In reality, of course, you cannot get everything you want, so you have to make trade-offs between these three properties. That's what leads us to a memory hierarchy where we have um, uh, these three properties satisfied to different extents. So in the memory hierarchy, at the top of the memory hierarchy, you will have small amounts of very fast but very expensive memory, and these are known as cache. In the next level, you will have some medium speed, medium priced memory, which is usually the DRAM or dynamic random access memory. And finally, at the lowest level, you can have slow but very cheap and large amounts of memory. And this corresponds to the hard drives or persistent storage devices that come with every computer. So, memory management component of the operating system is responsible for managing this memory hierarchy and for moving data back and forth across this hierarchy. So this is a pictorial illustration of the memory hierarchy. It's also an approximation of the memory hierarchy in modern computer systems. So at the top of the hierarchy, we have registers which are very fast because they are accessible at the granularity of nanoseconds, but they're also very small. You can only store small amounts of non-persistent data in these registers. Close to the registers, there are hardware caches such as L1 cache, L2 cache, L3 cache. And again, L1, L2, and L3 cache are themselves have different amounts of capacity and different access latencies. But the access latencies are still in the order of nanoseconds. Following the cache, we have the main memory, which is much larger than the cache, but it is also it also has reasonable access times. So the CPU is able to access the main memory through the system bus at reasonable latencies, which is about tens of nanoseconds. Then you have at the next level you have magnetic disks, which are hard disks, and now these days you also have solid state devices or flash drives that are much slower to access, but they have huge amounts of capacity. So till you reach the hard drives, all the memory that we have discussed so far is non-persistent or non-volatile, meaning that if you power off the computer, then the data vanishes. Whereas with storage devices such as magnetic disks, the data is persistent. If you write a piece of data, then it stays there till you erase it. So, and finally, after the magnetic disk, there are magnetic tapes. The magnetic tapes are sort of a legacy type of device where you essentially write data literally on a tape, and you can read and write to the tape sequentially. So it turns out that magnetic tapes, although they are very slow to access, but they have huge amounts of capacity. And if you, as long as you read and write data sequentially, they give you high throughput. So magnetic tapes are still useful for large volume, high throughput sequential read write operations. This figure shows three different ways of organizing memory when you have only one process running on the system. So in the first figure A, you have the operating system loaded into the initial part of the DRAM, or dynamic random access memory, and then the user program uses the rest of the main memory. In the second picture, operating system is loaded on the highest address space of the memory. But in this case, the highest address space, part of the highest address space corresponds to read-only memory. So this is very common in embedded systems, where a part of the address space is designated to a ROM, or read-only memory, where the operating system resides, and then the user program operates in the read-write part of the main memory. And figure C shows operating system loaded in the initial part of the main memory, as in figure A. But then in addition to that, you have device drivers that may be loaded in the read-only part of the main memory. And the user program occupies the rest of the memory. This is an example where now you have multiple processes that want to share the main memory. And this figure again shows two simple ways of sharing the main memory among multiple processes. So there is an assumption here that we want to have the entire process sitting in the main memory, the data for an entire process sitting in the main memory. So accordingly, we divide up the main memory into several partitions depending upon how large we expect each program to be. So we have four partitions of different sizes. Partition 1 and 4 are of the same size, and partition 2 is slightly larger, and partition 3 is the largest one. So we have two schemes for allocating processes to memory partitions, depending on how much memory they want. So the first scheme, shown in figure A, has three processes waiting for access to partition 1, one process waiting for access to partition 2, and two processes queued for access to partition 4. And there are no processes waiting for partition 3. So this is very similar to how you check out from a grocery store. So you have many checkout counters, and depending on how many groceries you have, you may go to one of the counters and wait for your turn. So this scheme um, has the advantage that you essentially allocate processes according to the size of the partition, and and if a large process comes along, it has a large partition available as soon as it needs it. So for example, if you have a process that needs large amount of memory, it will go to partition 3. But the disadvantage is that you might not make the most efficient use of resources. For example, although there is partition 3 in this example is idle, but none of the other processes can use it because they are stuck in other queues. Again, it's very similar to the grocery store analogy. If you might be stuck in one of the checkout counters, while there may be another checkout counter that becomes free. So um, to have a better usage efficiency, some people may use a queuing system shown in figure B, where you have a single queue of all the processes, and processes are picked from this single queue for any partition. So as soon as a partition becomes free, the memory manager would go through this queue and pick the next available job that would fit into that partition. So again, you can have different algorithms. You can pick the biggest job that can fit in the partition, or you can pick the very first job that can fit in a idle partition. And each of them can give you different levels of efficiency. And again, if you go to certain bookstores, for example, Borders or Barnes and Nobles, you might find the second scheme of queuing used for checking out, because you may have a single queue of people who are checking out from multiple counters. Next, we come to the concept of relocation and protection. The problem here is that at the time you write your program as a programmer, You don't know ahead of time where in the main memory your program will be loaded. So most programmers would assume that the memory addresses for their program start from address 0 and they go up to a certain limit. So depending upon the architecture, you may assume that the memory limit is 2 to the power 32 bytes or 2 to the power 64 bytes, whether the architecture is 32 or 64 bytes. Uh, but then when you're actually running the program may be loaded at some arbitrary location in the main memory. So, so this is known as relocation, where at runtime the program may be loaded at some offset. So in the second figure here, you have the program loaded at the base address, and the program's contents go up to base plus limit. Again, this is a very simple representation of how virtual memory works, but it illustrates the concept of relocation. The programmer assumes that the address space varies from 0 to a limit, whereas when it's loaded in the physical memory, the address may start from a base and go up to a limit. These concepts get more sophisticated as we will discuss both virtual memory and segmentation. But for now, it's important to understand that the programmer's view of base and limit is different from the actual base and limit that may be allocated to the program at runtime. In addition, there's also the concept of protection that's illustrated here. So the program is allowed to access memory only up to the limit. What if the program tries to access an address greater than limit, for example, limit plus 1 or limit plus 10 or byte at limit plus 100? So in such cases, the access should be disallowed because that memory doesn't belong to the process. So hardware for most computers would include some sort of a protection mechanism where if every memory access would be monitored, if the memory access goes beyond the limit, then the memory access would be disallowed by the execution hardware. In such cases, usually a trap is raised and the trap would transfer control to the operating system, which would usually terminate the process. So this is often seen by errors such as segmentation violation. When you run a program and your program may crash saying segmentation violation. So that usually means that you tried to access a memory location beyond the limit. Next, we are going to look at the notion of swapping. Swapping comes in when the amount of physical memory available is not enough to satisfy the demands of all the processes, which means that you have less physical memory than what is actually needed by all the processes together. So, as an example, let's say you have process A that's running in the main memory as shown in figure A. And then process B comes along, it takes up some more memory, then process C comes along and takes up some more memory. At this point, there is not enough free memory to accommodate process D. The free memory is shown here by the shaded area. So in order to accommodate process D, one of the existing processes has to be swapped out. Swapped out meaning that the contents of the process would have to be written to the disk, and then an additional empty space would be created, which would then be used by process D. So in this example, in figure D, we notice that process A is being swapped out. And once process A has been saved to the disk, then that space is allocated to process D, which happily continues executing. So after some time, we want to bring back process A, so we have to create more space. So we swap out process B and bring in process A, and so on. From this point on, anytime a new process has to be scheduled, you'll have to swap out a certain process to bring in the new process. So, so the terminology here, as you may have noticed, is swapping in a process and swapping out a process. Swap in and swap out. So the terminology swapping in, swapping out is used for entire processes. When an entire process is moved out of memory or an entire process is brought into memory. Later, we will also see that parts of a process can be moved in and out of the main memory. You don't have to shift out an entire process from the main memory because taking out an entire process from the main memory is a very expensive operation. So swapping in and swapping out is necessarily very slow. Now let's look at how the operating system manages the main memory when the total demand on the main memory is larger than the amount of available DRAM. The figure shows two views of the memory. The first is the view of a process, which looks at the memory as a virtual address space, beginning from 0 to a maximum value. Whereas the second figure is the view of the physical memory as seen by the operating system. This is the total physical memory available in the system. So the job of the operating system is to take the virtual address space of every process and map it to the physical memory. Now, in order to do this, the operating system divides up both the virtual and the physical address spaces into equal sized units called pages. Why do we break up the virtual memory into pages? Because it allows the operating system to keep only those parts of the virtual address space in the main memory that the process really needs. If a process is actively using some part of the virtual address space, then those virtual pages would be mapped to physical memory. Rest of the pages would be stored elsewhere, for example on the hard disk. Some parts of the address space may not even be allocated unless the process tries to use those virtual pages. This figure shows the various components of memory address translation mechanism. There is part of the hardware which sits alongside the CPU called Memory Management Unit or MMU. MMU's job is to translate virtual addresses issued by a process into physical memory addresses. The virtual addresses are provided as input to the MMU. Then the MMU performs some mapping to convert the virtual addresses into physical memory addresses. These physical memory addresses are then sent over the system bus to the memory controller, which then accesses the corresponding memory locations. So how does MMU perform translation from virtual to physical memory addresses? So there's a data structure which is very central to all the memory management and operating system. This data structure is called page table. Every process in the operating system has a page table. So the purpose of page table is to map virtual memory to physical memory. As we discussed earlier, the virtual address space is broken up into equal sized pages. Every page in the virtual address space needs to be mapped to the physical memory at some point in time. However, the physical memory may be smaller than the total virtual address space. Hence, only some of the virtual pages can be mapped to the physical memory at any point in time. So the page table keeps track of where each page in the virtual address space is located. Either the virtual page would be located or mapped to the physical memory, or it may be swapped out and kept on the hard disk, or it may not be allocated at all. So in this example, we see that virtual page number 0 is mapped to physical page number 2. Similarly, virtual page number 1 is mapped to physical page number 1. Virtual page number 2 is mapped to physical page number 6, and so on. At, however, some of the pages are not mapped to the physical memory, which means that they are not present in the physical memory. These mappings are marked by an X in this figure. What this means is that the pages are not present in the main memory, rather they are either swapped out or they have not yet been allocated. Now this figure shows how the memory management unit translates a virtual address to a physical address. So the virtual addresses are provided as input to the MMU, and the output is a physical address that is placed on the system bus. When a virtual address arrives at the bottom of this figure as input to the MMU, the virtual address is broken up into two components. Some of the bits represent the page offset and other bits represent the page number. So in this picture, we have a 16-bit virtual address which is being converted into a 15-bit physical address. The 16-bit virtual address allows you to address 2 to the power of 16 bytes or 64 kilobytes of virtual memory, whereas 15 bits of physical address allow you to access 2 to the power of 15 bytes of physical memory or 32 kilobytes of physical memory. So we assume that each page here is 4 kilobytes in size. 4 kilobytes 4 kilobyte pages require at least uh, 12 bits to access each byte in the page. So what that means is that in a 4 kilobyte page there are 2 to the power of 12 bytes. So in order to address 2 to the power of 12 bytes, you need 12 bits. Thus the lower 12 bits of the virtual address are used as page offset. These bits are directly transferred to the output without any translation. Out of the 16 bits of virtual address, the remaining 4 bits, or the most significant 4 bits, are used as an index to look up into the page table. So in this picture you would see that the most significant 4 bits are used to index the page table to find out what is the corresponding physical page number. So if the table in the middle of the MMU is the page table, so in this case there are two entries in the page table. The first entry is the physical page number corresponding to each virtual page, and the second entry is a present absent bit. A 1 indicates that the corresponding page is present in the main memory, and a 0 in the present absent bit indicates that the page is not present in the main memory, or that the end page table entry is invalid. So in this example, the virtual address or the virtual page number here happens to be 2. So we use the last 4 most significant 4 bits to access the second and the third entry in the page table, or the entry at index 2, and we find that the corresponding physical page number is 110 or 6. So since the present absent bit is 1, it means that this entry is valid. The 3 bits representing the physical page are then transferred to the output and appended to the 12 bits that we had directly transferred from the page offset. So the 12 bits of the page offset and the 3 bits of the physical page number together give us the 15 bits for the physical address being accessed. Now in this example, we had only 16 bits for the virtual address, which meant that with 4 kilobyte pages, we had only 16 pages in the entire virtual address space. So uh, so the page table itself contains only 16 entries, one for each virtual page in the virtual address space. Now this is a very small page table, and it's very easy to have enough memory in the MMU to accommodate the entire page table, right? But if you increase the size of the virtual address space, so let's say in a 32-bit architecture, then you would find that the page table size also increases. For example, if you had 32 bits for virtual address and 4 kilobyte pages, then you would have 12 bits for the page offset, which leaves 20 bits for the virtual page number. So your page table would need to have 2 to the power of 20 or a million entries. If you go even further to 64-bit architectures, then the number of page table entries would increase significantly. Now it's clear that for very large page tables, all the memory cannot be placed inside the MMU. So what do we do? The solution is to take the page tables out of the MMU and keep them in the main memory. Main memory has a large amount of capacity, so storing large page tables in the main memory is not a problem. In addition, memory for page tables can be allocated as and when the page tables grow. Now, instead of storing the entire page table in the MMU, we can replace the page table with the page table base register that holds the base address of the page table. Every time there is a process context switch, we need to change the page table base register to point to the new address of the page table for the new process. Now let's take a look at how the page table works for a 32-bit architecture. This is specifically the Intel architecture where, where Intel provides two levels of page tables. So given 32 bits of virtual address, we divide up the 32 bits into three parts. A 12-bit offset into the page and two 10-bit indices. So the first 10-bit index is used to look into a top level page table, this is also known as a page directory. The page directory then provides the base address of a second level page table. So the next 10 bits of the virtual address are then used to look up the second level page table. And finally, at the second level page table, the corresponding entry gives us the base address of the page that we are trying to access. The page itself is shown by a small rectangle at the very end of the figure. Now, once we have the base address of the page, we can use 12 bits of the offset to access the specific byte that we need to read or write. Now remember that all this translation is done in the hardware. So the entire translation from the virtual address to the physical address is done in the hardware by the MMU. MMU has access to the page table base register, which provides the base address of the top level page table. The page table base register is also known as the CR2 register on Intel architecture. Now another way to understand this figure is to consider the page table as a giant array. Okay, it's essentially a giant array where every entry of the array is a page table entry. So if you were to allocate the whole array in one shot, then that would be very inefficient. First of all, you won't find enough memory to accommodate the entire array, and even if you did, it is kind of wasteful because most of the entries in the page table may never be used. The process may never access the pages that correspond to most of the entries. So we want to allocate the page table in a dynamic fashion, meaning as the memory demands of a process increases, we would allocate more and more parts of the page table. So one way to do that is by breaking up the page table into several chunks, and these chunks are represented in the second row in the figure. So um, so we allocate page table in incremental chunks of 4 kilobytes each. And how do you keep track of these different parts of the page table array? For that, you have the top level directory. And top level directory keeps track of where each of the individual components of the page table are located. So essentially, the whole data structure is simply a large array that has been broken up. Different parts of the array are stored in different parts of the main memory, and the top level page table keeps track of the different parts of the page table. So that's pretty much all it is. A page table is essentially a giant array that has been broken up and stored at different places in the main memory. Next, let us look at what each page table entry looks like. This is just a typical format of the page table entry. Different architectures will have different formats, but their main components would mostly be the same. So the most important component of a page table entry is the physical page number or the page frame number. So in um, architecture terminology, a physical page is also referred to as a page frame. So in addition to the physical page number, there is an additional bit called the present absent bit. The present absent bit, as we discussed earlier, it indicates whether the corresponding virtual page is present in the main memory or it's absent, meaning swapped out or unallocated. Then we have certain protection bits that specify what are the permissions for access to this page. For example, a process may have permissions to read a page or write a page or execute the contents of the page. So these privileges are controlled by the operating system. Now, there is also an additional bit called the modified bit. This is also called a dirty bit. And then there is another bit called referenced bit. Referenced and modified bit go together. The purpose of the referenced bit is to track whether the page has been accessed recently. Periodically, the operating system would go around and reset all the referenced and modified bits. As a process accesses the pages, the reference bits would be set. If a process writes to a page, then the modified bit would be set. This way, the operating system can go back and examine these bits once in a while and figure out which pages are being actively referenced and which pages have been written since the last time these bits were reset. So there is a very important role that these bits play because it allows the operating system to determine which pages are important for the process and which pages are not. The pages which are not being accessed can then be swapped out of the main memory and written to the disk. Finally, there is a caching disabled bit that is used by the operating system for memory mapped IO operations. We will discuss memory mapped IO later when we talk about IO subsystem, but the basic purpose here is to tell the virtual memory system not to cache these pages. The operating system itself maintains a file system cache, and for memory mapped IO operation, we don't want to cache the contents of those pages. We really want the content, the read and write operation on the pages to be sent to the IO controllers. Now let's take a look at another important component of the memory translation hardware called the translation look aside buffer or TLB. So the purpose of TLB is to speed up the memory translation from virtual addresses to physical addresses. Remember that several slides ago we saw an example of uh, of a memory translation unit inside the MMU. So inside the MMU we had a small page table. Since when the page table got too big, we moved the page table out to the main memory and replaced it with a register or a page table based register. Now, what that meant was that every time the MMU had to translate a virtual address, it would have to use the page table based register to access the first level page table, then the second level page table, and finally the byte offset inside the page, which meant that for every memory access, you were incurring two additional memory accesses for the page walk, for the page table walk. So that can be very expensive because now essentially we're adding a 200% overhead on top of regular memory access times. To if that was the case, then most of our programs would run very slowly because memory accesses would be really slow. But obviously our programs run fast, and the reason for that is that there's an additional piece of hardware called the TLB that speeds things up. So TLB is like a cache, but it's not a data cache. It is a cache of the translations from virtual addresses to physical addresses. So TLB is part of the MMU. So when we took out the page table from the MMU, we replaced it with a small TLB. So TLB is used to store the frequently accessed translations from virtual to physical addresses. So whenever the MMU performs a page table walk, it takes the virtual to physical page table mappings and stores them in the TLB. Thus, TLB is a repository for frequently accessed page table translations. So let's take a look at an example. Here we have a TLB that has a valid invalid bit which indicates whether each entry in the TLB is valid or invalid, and then there is a virtual page number and a physical page frame number. So for example, virtual page 140 is mapped to physical page 31, virtual page 130 is mapped to physical page 29, and so on. In addition, you also have the dirty bit, which is stored here, then the protection bits that are used to determine whether a particular access is allowed or not. So since TLB is part of the MMU, it's part of the hardware, so TLB cannot be very large. In fact, this is um, it consists of a very fast associative memory in which whenever you get a virtual page number, you can search all the entries in the TLB at the same time. So this provides a very fast search operation, but because it's a very fast associative memory, it's also very expensive. So larger the TLB size, the more expensive your memory translation hardware becomes. Now there are two types of memory translation architectures: architected page tables and architected TLBs. In architected page tables, the format of the page table is defined or specified by the ISA, or the instruction set architecture. So the hardware specifies what a page table should look like, and the entire page walk is handled by the memory management unit. The MMU handles a TLB miss. If there's a TLB miss, the MMU would perform a page walk, retrieve the physical page address, and directly ask the memory controller to access the specified memory location. If there is a page fault, which means that program accesses a page that has not yet been mapped in the page table, then the operating system is notified through a page fault exception. So on the other hand, there is a different architecture for memory translation called architected TLB. Here the instruction set architecture only specifies the TLB interface. The contents of the TLB can be controlled by the operating system. Now, if there is a TLB miss, then the MMU does not perform a page table walk. In architected TLBs, when a TLB miss occurs, the operating system is notified via a trap, and then the operating system figures out how to handle the TLB miss. This provides the operating system with greater control over the contents of the TLB. An example of architected page table is Intel's x86 architecture, where the page table format is closely specified by the ISA. An example of architected TLB is the Alpha architecture, which is now obsolete. Now let's revisit the concept of a cold start penalty. We had learned earlier that immediately after a context switch, a process may perform in a degraded manner. Its performance may not be its peak performance. This is because most of the hardware caches are cold. Specifically for TLB, what this means is that any translations that the process needs from virtual to physical addresses, those translations have not yet been stored in the TLB. So immediately after a context switch, the process may go through a series of TLB misses till enough TLB entries have been populated by the MMU. At that point, the process can start executing full throttle at its peak performance. So the cold start penalty is roughly the cost of repopulating the TLB and other hardware caches upon a context switch. Now there is a concept called tagged TLB, which means that every TLB entry has an associated tag. The purpose of the tag is to identify the process with which a specific page table translation is associated. So the execution context could be either that of a process or a thread, or in any other way the operating system defines an execution context. Thus, when you perform a context switch, the hardware does not need to flush the entire TLB. This way you can keep the old entries of a process being switched out, so that if the process comes back in the near future, then it will still find that some of the TLB entries are present. So thus a tag allows the TLB to avoid a full TLB flush upon a context switch. Now let's take a look at the impact of the page size on the page tables. So if so far we have dealt with standard page sizes of 4 kilobyte, but in fact the page size could be larger or smaller depending upon the system configuration. So there are certain advantages and disadvantages of small page sizes, or conversely large page sizes. If you have small page sizes, then there is less internal fragmentation. What that means is that if you allocate a page to a process and the process doesn't use the entire page, then the rest of the page would be wasted. With small pages, the amount of wastage or the amount of internal fragmentation is less. If you allocate a large page and let's say the page only uses a few bytes, then the rest of the page cannot be used by other processes. The second advantage of a small page size is that page in and page out operations are less expensive. When the operating system decides to swap out a page from the main memory, then the overhead of doing so is less. On the other hand, there is a disadvantage of small page sizes. The smaller the page size, the more are the number of pages in the virtual address space. And since every page needs a page table entry, so it means that smaller pages would result in large page tables, which means that the page tables would have lots of entries. So ideally, a system should try to find a balance in between the amount of internal fragmentation and the size of the page table. Now, this also brings us to the concept of TLB coverage. TLB coverage refers to the amount of the main memory that is addressable or translatable from the TLB. So TLB has a fixed number of entries. Every entry provides translation for one page. So a TLB coverage is equal to the number of TLB entries n times the size of each page p. So n times p bytes. Now since n is fixed by hardware constraints, so the only way to increase TLB coverage is to increase the size of the page p. Now, why do you want to increase the TLB coverage? Note that if you have a larger TLB coverage, it means that more of the main memory can be covered by the TLB, and thus you would have fewer TLB misses. Fewer TLB misses means fewer page table walks by the MMU, which means faster memory access. So a large TLB coverage is very good for performance of the applications. Now, to consider how the TLB coverage works. Suppose you take some extreme examples. Suppose you have a page size of 1 byte. All right. So So in this case, the TLB coverage, according to the formula, will be n bytes only. So of the entire main memory, you can only access n bytes without any TLB misses. On the other hand, suppose on a 64-bit architecture, a size of a page is 2 to the power of 64 bytes, okay, which is again like a very impractical example, but just for argument's sake. Then the TLB coverage would be the entire virtual address space of the process, right? So which means that the entire virtual address space of the process can be covered by one TLB entry. And if you have n TLB entries, then essentially n processes can have their entire address spaces covered without any TLB misses. So obviously these are two extreme examples. More realistically, you would like to have a page size that provides you a reasonable TLB coverage, um, and, and at the same time it doesn't increase internal fragmentation too much. This brings us to the concept of super pages. So hardware designers understood that sometimes operating systems would like to increase the TLB coverage by using larger page sizes. So instead of just providing one page size, most architectures provide multiple page sizes. In some cases, when it makes sense, operating systems may choose to increase the size of a page. So these pages that are bigger than normal pages are known as super pages. A super page size is usually the power of 2 times the base page size. For example, um, a super page may consist of one base page or two base pages or four base pages or eight base pages and so on. Now, there is usually only one TLB entry per super page. So this is what increases the TLB coverage. Uh, although there is only one TLB entry for every super page, each base page still has a separate page table entry. However, all the page table entries for the base pages are identical, which means that they have the same base address for the physical page and the same number of bits used to access the offsets within the superpage. In addition, superpages come with several constraints. You cannot arbitrarily create a superpage anywhere in the main memory for whatever size you want. All the base pages of a superpage have to be contiguous, meaning that they should be next to each other in both the physical memory and in virtual address space. Similarly, all the base pages must be aligned, meaning that they should start at an address that is the multiple of the superpage size. For example, a superpage of size 8 of size 8 base pages can start only at offset 0 or offset 8th base page or offset 16 base pages and so on. So it cannot start at offset 5th base page or offset 10th base page because these are not multiples of 8. All the base pages of a super page have uniform protection attributes, which means that either all of them are read-only or all of them are read-write or all of them are executable. Different base pages cannot have different permissions. Finally, there is only one reference bit and one dirty bit to track accesses to the entire super page. The operating system cannot distinguish which base pages were accessed more or less than the other base pages of a superpage. This figure shows a simple example where a superpage of size 4 is in the virtual memory is mapped to a superpage of size 4 in the physical memory. So normally for every base page shown in the green color, there is one TLB entry which maps it to the corresponding physical page. Similarly, for a super page, although there are four base pages, there is only one TLB entry that maps it to the corresponding physical page in the physical memory. The only difference between a normal page and a super page is that there is an additional field in the TLB which specifies that this is a super page of size 4 instead of size 1. As mentioned earlier, different architectures provide super pages of different sizes, and here we show some example super page sizes for alpha and Itanium architectures. As you can see, operating systems can create really large super pages if they choose to do so. Here is a quiz that tests some of your basic skills in understanding the page table, page size, byte offsets, and the relationship of these concepts. So please work through these examples on your own. There is also the solution to this quiz in the next slide. So if you have any questions about the quiz or the solutions, feel free to ask me or the TA. And here are some references to help you better understand the material that we have just discussed.